Stainless steel doesn't rust. It's one of those things most of us accept without ever questioning. We buy stainless steel water bottles because we expect them to last forever. We choose stainless steel kitchen knives because they promise durability. We install stainless steel sinks, appliances, and railings because they're supposed to resist corrosion. But sooner or later, almost everyone has the same confusing experience. A supposedly stainless spoon develops orange spots. A stainless steel barbecue starts showing rust after just one rainy season. Even expensive stainless steel screws can corrode until they're almost unrecognizable. So, what happened? Were manufacturers cutting corners? Was it fake stainless steel? Not necessarily. The real surprise is this: stainless steel was never meant to mean rust-proof. It simply means stains less. That tiny difference has created one of the biggest misconceptions in modern manufacturing, and it affects everything from the cutlery in your kitchen to the skyscrapers towering over today's cities. Once you understand why stainless steel comes in so many different grades, you'll never look at this everyday metal the same way again. The story begins more than a century ago, in an unlikely place. In the early 1900s, Europe was rapidly industrializing. Factories were producing machines faster than ever before, but engineers faced an expensive problem. Steel was constantly rusting, not just bridges and buildings. Factory equipment, chemical tanks, food processing machinery, and even military weapons all suffered from corrosion. Rust wasn't merely an inconvenience. It cost industries enormous amounts of money through maintenance, repairs, and replacements. Scientists across Europe searched for ways to make steel resist corrosion. Many experimented by adding different elements to ordinary carbon steel. Nickel, tungsten, manganese, vanadium, each improved certain properties, but none solved the rust problem. Then came chromium. In 1913, English metallurgist Harry Brearley was working in Sheffield, a city famous for steelmaking. Ironically, he wasn't trying to invent kitchen cutlery. His assignment involved developing more durable steel for gun barrels, which rapidly wore out under intense heat and pressure. Brearley experimented with steel containing unusually high amounts of chromium. Many of his test samples failed their intended purpose, but something unexpected caught his attention. Months later, discarded samples lying outdoors had barely rusted at all. That observation changed metallurgy forever. Brearley realized chromium wasn't merely strengthening steel, it was protecting it. Here's the fascinating part. Steel is mostly iron. Iron naturally reacts with oxygen and moisture. That's rust. It's one of the most common chemical reactions on Earth. So, why does chromium change everything? The answer lies in an invisible layer only a few atoms thick. When steel contains roughly 10.5% chromium or more, the chromium reacts with oxygen before the iron does. Instead of forming flaky rust, it creates an incredibly thin layer of chromium oxide across the surface. You can't see it. You can't feel it. Yet this microscopic shield blocks oxygen and water from reaching the iron underneath. Even more remarkable, if the surface gets scratched, this protective film can reform by itself as long as oxygen is present. It's called a passive layer, and it's one of the most elegant examples of self-protecting materials in modern engineering. Without it, stainless steel simply wouldn't exist. But here's where the misunderstanding begins. That protective layer isn't magic, it's chemistry, and chemistry has limits. If the environment becomes too aggressive, the protective film can break down faster than it repairs itself. Saltwater, industrial chemicals, acids, high temperatures, poor maintenance. Even microscopic contamination from ordinary carbon steel can damage the surface under the right conditions. This is why two pieces of stainless steel sitting side by side can behave completely differently. One remains bright for decades, the other begins rusting within months. The difference often isn't quality, it's the grade. And that's where most people unknowingly make expensive mistakes. Walk into almost any hardware store and you'll see products simply labeled stainless steel. No explanation, no details, just one reassuring word. But that label hides an enormous amount of engineering. There isn't one stainless steel. There are hundreds. In fact, engineers have developed well over 100 standardized stainless steel grades, each designed for a specific purpose. Some are optimized for strength, others prioritize corrosion resistance. Some survive inside chemical plants, others are designed for surgical instruments. Some can withstand temperatures hot enough to glow red. Others are made to be shaped into thin kitchen sinks or automobile trim. Calling them all stainless steel is a little like calling every vehicle simply a car. A compact city hatchback and a heavy-duty mining truck are both vehicles, but they're built for completely different jobs. The same is true for stainless steel. The name stays the same. The performance can be worlds apart. And understanding those differences begins with two numbers you've probably seen countless times, but may never have questioned. 304, 3 and 16. At first glance, they seem like meaningless model numbers. In reality, they represent one of the most important material choices in modern manufacturing. And as you'll see next, one small change in chemistry can mean the difference between a product that lasts a lifetime and one that quietly begins to fail. Those two numbers, 304 and 316, appear everywhere, yet most people never notice them. Look closely at high-quality cookware, marine hardware, laboratory equipment, or premium water bottles, and you'll often find one of these grades hidden in the specifications. To most buyers, they're just numbers. To engineers, they tell an entire story. The world's most common stainless steel is 304. It accounts for well over half of all stainless steel produced globally. Walk into a modern kitchen, and chances are your sink, refrigerator, cookware, or cutlery contains some form of 304 stainless steel. There's a reason it's everywhere. It offers an excellent balance of corrosion resistance, strength, workability, and cost. For most indoor environments and everyday use, it's more than capable of lasting for decades. So, why would anyone pay more for 316? The answer is one element that makes up only a tiny fraction of the alloy: molybdenum. Typically added at around 2 to 3%, molybdenum dramatically improves resistance to one of stainless steel's greatest enemies: chlorides. Chlorides are everywhere. They're in seawater, road salt spread during winter, swimming pools, even human sweat. When chloride ions settle on stainless steel, they can attack the protective chromium oxide layer. Instead of causing widespread rust, they often create something more dangerous: tiny localized holes known as pitting corrosion. At first, these pits are almost invisible, but beneath the surface, they can grow deeper and deeper, weakening the metal while leaving much of it looking perfectly fine. It's a silent form of failure, and it has caused everything from leaking pipes to damaged boats and industrial equipment. That's why you'll find 316 stainless steel on ships, offshore oil platforms, coastal buildings, medical instruments, and food processing equipment that must withstand harsh environments day after day. The extra cost isn't paying for shinier metal. It's paying for chemistry that survives where ordinary stainless steel begins to struggle. But here's another misconception. Higher grade doesn't always mean better. Imagine buying racing tires for your family sedan. They're engineered to perform under extreme conditions, but they're more expensive, wear differently, and provide little benefit for everyday commuting. Materials work the same way. An engineer doesn't ask, "What's the best material?" They ask, "What's the right material for this job?" A kitchen knife requires different properties than a bridge cable. A surgical scalpel demands different characteristics than an exhaust system. Even within stainless steel, every grade represents a compromise. Some maximize corrosion resistance, others increase hardness, some improve weldability, others reduce manufacturing costs. There is no perfect stainless steel, only the right balance for a specific application. This philosophy explains why stainless steel continues to evolve more than a century after its invention. Today, engineers have developed specialized families of stainless steels, each solving a different challenge. Ferritic stainless steels contain little or no nickel, making them more affordable and commonly used in appliances and automotive components. Martensitic stainless steels can be heat-treated to become extremely hard, making them ideal for knives, scissors, turbine blades, and surgical tools where sharp edges matter. Duplex stainless steels combine high strength with exceptional corrosion resistance, allowing chemical plants and offshore platforms to reduce weight without sacrificing durability. Some advanced grades are even engineered to survive inside nuclear reactors, desalination plants, and spacecraft. The name remains the same, but the science keeps advancing. And yet, despite all this engineering, stainless steel still has one weakness: people. Many cases of rusting stainless steel have nothing to do with the alloy itself. A stainless steel sink scrubbed with ordinary steel wool can become contaminated with tiny carbon steel particles. Those particles rust, creating orange stains that make people think the sink is corroding. Construction workers sometimes use the same grinding tools on carbon steel and stainless steel. Microscopic fragments transfer from one material to the other, creating future corrosion sites. Even fingerprints can matter. Human sweat contains salts that, if left on certain stainless steels in harsh environments, can eventually contribute to staining. Engineers know that selecting the right grade is only half the battle. Proper fabrication, cleaning, and maintenance are just as important. Perhaps that's the biggest lesson stainless steel has to teach. Materials are rarely defined by simple labels. Marketing gives us easy words. Engineering reveals complex realities. The word stainless sounds absolute. Nature doesn't deal in absolutes. Every material has strengths. Every material has limits. The real challenge isn't finding something that never fails. It's understanding the conditions under which it succeeds. So, the next time you pick up a stainless steel water bottle, wash dishes in a stainless steel sink, or admire the gleaming facade of a modern skyscraper, remember what you're really looking at. Not a miracle metal, not a rust-proof alloy, but over a century of scientific discovery, metallurgical innovation, and careful engineering. A material that protects itself with a film so thin it's invisible. A material that can repair its own surface under the right conditions. A material available in hundreds of carefully designed variations, each solving a different problem. And perhaps the biggest surprise of all? The lie about stainless steel was never that manufacturers were trying to fool us. The lie was the assumption that one word could describe one material. In reality, stainless steel isn't a single metal at all. It's an entire family of alloys, each with its own strengths, weaknesses, and purpose. Once you understand that, those tiny numbers, 304, 316, 430, 2205, stop looking like meaningless codes. They become evidence of one of engineering's greatest achievements, the art of designing the right material for the right job. And that's why more than 100 years after its accidental discovery, stainless steel remains one of the most important and most misunderstood materials ever created.